So our topic for today is about the stress, strains, and the Young's modulus. And it's a common topic for both Edexcel and the Cambridge students. So how we define the term, first starting with the Hooke's law. So what is the Hooke's law? It states that within the limit of the proportionality, the extension of a spring is directly proportional to extension or a compression of a spring is directly proportional to applied force. Means if I apply a greater force on the spring, say a spring is there of length L naught, and we add a load, we call W or F. The new length of the spring is L. Extension means an increase in length, so it is the new length minus the original length will get the extension. So according to Hooke's law, that the extension of the spring is directly proportional to the stretching force. If we apply a greater stretching force, then we'll observe the greater change in the length. But the proportionality relation is only valid to a certain point. We call that as a limit of proportionality. So if we sketch a graph between the force and the extension, the graph will start from whenever two quantities are directly proportional, the graph will start from the origin and it will be a straight line. The last point where this relation is valid, we call that as a limit of proportionality or the proportionality limit. What does it mean, the term proportionality limit or limit of proportionality? It means if we double the force, for example, when there was no force was acting, the extension was 0. When we apply a force of 10 Newton, the extension is 2. When we double the force, extension is double. When we triple the force, extension is 3 times the original. But when force is 5 times the original value, like originally it was 10, now 50. So extension should also be 5 times, but we don't have 5, like we have 11. So means this 50 and 11 is beyond the limit of proportionality. It means we cannot apply the Hooke's law here because Hooke's law is only valid within the limit of proportionality. So within the limit of proportionality, force or the load which is applied on the spring is directly proportional to the extension, or extension is directly proportional to the applied force. Whenever we replace the proportionality sign, we always replace with equal to and a constant. So here we have a constant of equation which is known as the spring constant. So this case refers to a spring constant or the stiffness. And when we talk about the force of the spring, because force of the spring is always a restoring force, like the spring always like when you add a load to the spring stretches. So which direction the force is applied by the string is always to return to its original position. That's why it is written F is equals to minus K delta X, or you can also say E, which is extension. So here the force was 10, extension is 2. When we double the force, like force is twice, extension is also twice. When we triple the force, like 10 multiplied by 330, the extension is also 3 times. When it's quadruple, means multiplied by 4, this is also multiplied by 4. But when it is 50, it's multiplied by 5, the extension should be 10, but it's not 10, it is 11. So it means that it is beyond the limit of proportionality. So why there is a negative sign for this? The negative sign shows that the force of the spring is always opposite to the force which we applied. Like example, if we applied the force F, what will the direction of the force of the spring is to restore? So it will be negative F. That's why it is this negative sign only shows that the force of the spring is always restoring force. It always try to move the spring, return to the original position or original length. So within the limits, the extension of a spring, or it's not only about extension, it's also about compression. The compression of the spring is also proportional to the force applied. So we have a spring and it is subjected to a force F. So the term compression means the reduce in length. So how much the length has reduced? Like example, the original length was L naught and the new length is L. So how much is a compression of this spring? So it will be L naught minus L. And according to Hooke's law, the compression is also directly proportional to the force applied on the spring within the limits of compression. Why? Because there's a limit to which you can compress. You cannot reduce something to a size 0. So in this case, in a compression, the original length will be more and the new length will be less. That's why it is L naught minus L. But in the extension, the original length is shorter and the new length, it will be longer. That's why it will be, the extension will be L minus L naught. So if I have a spring, experience of force F, and extension is there like in centimeter. And we have a straight line. Does this spring obeys the Hooke's law? Yes or no? So yes, this spring obeys the Hooke's law because it's a straight line and it is passing through the origin. If I sketch another graph between the force and the length, we have force and we have a length and it is a straight line. Does this spring obeys the Hooke's law? The second, between the force and the length graph? Does it obey the Hooke's law? This graph is between the length and the force. The answer is yes, it does obey the Hooke's law. But I cannot say, for this graph, I cannot say force is directly proportional to length. That is wrong. But what is happening? The increase in the length is same. When we increase the force, so it means yes, the extension or the increase in the length is same for every change in the force. So it means yes, it obeys the Hooke's law. So if you have a force and extension graph, it should start from origin and it must be a straight line. If you have a force and length graph, it must be a straight line. It will not start from origin because there will be some length of the spring when you add a load. So it should be a straight line. It will not start. And I can also say it obeys the Hooke's law because the extension increases by a same factor as the change in the length is same. So extension increases with the same factor as we change the force. So we'll say, yes, it obeys the Hooke's law. But I cannot say that force is directly proportional to length. That is wrong. That I cannot say that force and extension are directly proportional. Force and length are directly proportional. But I can say that the increase in the length or the change in length is proportional to the force. So when I calculate like increase in length, I calculate the extension here, or I calculate the extension for different change in the force, I'll get the same result. And if we have a force and extension graph, we can calculate two things from the force and extension graph. Number one is the spring constant, which is force divided by extension. But sometimes you may have a graph in which you have force on x-axis and extension on y-axis. For those graphs, if you need a spring constant, you have to use a formula that K is equals to F divided by E. But for the graph in which you need the spring constant and forces on y-axis and extension on x-axis, so what you can do, you can work out the gradient of the graph. Because the gradient of the graph is a quantity on y-axis divided by quantity on x-axis. So on y-axis, I have force, on x-axis, I have extension. So this will give us the spring constant. But if I work out the gradient of this graph, it will be the quantity on y-axis divided by x-axis. So on y-axis, I have extension. On x-axis, I have force. So extension divided by force is not the spring constant. It is a reciprocal of the spring constant. The second thing which we can calculate is the energy stored in the spring or work done on the spring or work done by the spring. So how we can calculate the work done by the spring is area under the graph. As I mentioned, area of the graph, what it represents, area of the graph is a product of quantity on y-axis into x-axis. So on y-axis, you have force, which is Newton. On y-axis, you have Newton. On x-axis, you have meter. So Newton meter is what? Newton meter represent the joules. So actually, when you take the area of this graph, what you will get a quantity which is known as energy. So whenever we want to find how much energy is stored in the spring or how much work is done by the spring, so we can use area under the graph. And for a Hooke's law, because the spring obeys the Hooke's law, so it will always form a triangle. And what is the area of the triangle? The area of the triangle is half base into height. So it will be half force into extension or extension into force. So when I take the area of this graph, I'll know how much energy the spring will store. And if I work out the gradient of the graph, I'll know the stiffness of the spring, or I can identify how much force I need to produce a 1 centimeter or 1 millimeter extension. Is it clear, this one? Any doubt? But sometime the object may not obey the Hooke's law, and we want to find, like the spring does not obey the Hooke's law, and we have to find what will be the gradient. If we take, it depends on the graph, because sometime, usually, not sometime, usually, they give the extension on y-axis and they give the force on x-axis. And one more important thing, the unit of the extension most of the time is in centimeter. So don't forget to convert into meters, okay? When you substitute the value, don't forget to convert into meters. So if I have extension on y-axis and force on x-axis, and I have a straight line graph, and I work out the gradient. So when I work out the gradient is a quantity on y-axis divided by quantity on x-axis. So on y-axis, I have extension. On x-axis, I have force. So in this case, my gradient will be reciprocal of the spring constant. And when I take the area under the graph, because the area under the graph is a quantity on y-axis into x-axis, so it will be extension into force. Means the extension is in meter and the force is in Newton. So meter Newton or Newton meter means I'll get the energy. And what is the shape of this graph? The shape of this graph is a triangle. So if I need the area, it will be half base into height. So area of the triangle, and that area of the triangle will give us the energy in joules. But don't forget to convert the centimeters into meters. But sometimes you may have the force on y-axis and extension on x-axis. In that case, the gradient will be equals to the spring constant. If we have a non-linear graph that the spring was obeying the Hooke's law, and then we cross the elastic limit, we cross the limit of proportionality. Limit of proportionality means the last point where we have a straight line between the force and extension. We call that as a limit of proportionality or the proportionality limit. Then there will be another point. As we increase the force, the extension will also increase. There will be another point which is called elastic limit. What is the difference between the elastic limit and the limit of proportionality? The elastic limit is actually refers to a point after which the spring will deform. Say we were having originally the spring was having a length of 10 centimeter. We add the load and the spring has stretched to a length of 12 centimeter by a load of say 100 newtons. When I remove the load of 100 Newton, if the spring returned to the same original length, it means we are within the elastic limit. But what if when we remove the load and the spring deformed, its new length is like 10.2 centimeter. So means we are beyond the elastic limit. We cross the elastic limit. So elastic limit is a point after which the spring will deform permanently or it will lose its shape or it will change its original length. So within the elastic limit, the object will return back to the same original length, but beyond the elastic limit, it will deform. And what we call that deformation, we call that as a plastic deformation. So if I remove the force before the elastic limit, it will be elastic deformation. Elastic deformation means it returned back to the same original length. But if I remove the load beyond the elastic limit, we call that as a plastic deformation or the spring has deformed permanently. So if we carry out a deformation for a spring, elastic or a plastic deformation, then the shapes of the graph will be different. Example, we have force and extension. We have force and extension. So first, the spring was obeying the Hooke's law. We call that as a limit of proportionality. The last point, it was obeying the Hooke's law. Then we increase the force, extension is also increasing. Say it is, this point is an elastic limit. If we return, if we start to unload, like unload, because this is a loading graph. Loading means we are adding the weight to the spring. We call that as a loading. When we start to unload, this will be the graph for unloading. Unloading means we remove the load. But why the loading and the unloading graphs are different from each other? Because what will happen? See, you have a spring, you are adding a load. So means you are doing work done on the spring, which is a product of force and distance. So what is the work done by you? That is how much force you applied and what is the distance move? Distance it moved. But what is the work done by the spring? The work done by the spring is always F into D divided by 2 because the area under the graph, which is normally a triangle. So area of a triangle is half base into height. So it will be 1 by 2 F into D. So when you are doing a work, like example, you did a work of 100 joules on the spring. But when you remove the load, the work done by the spring is always half of what you did. Not always half, but most of the time it's half what you did. So what it shows that the sum of the energy is left in the spring. That's why the loading and the unloading graphs will not be same. So when you are adding a load and when the spring is doing a work done, spring stores some of the energy. That's why the area of the loading graph and the area of the unloading graph will never be same. And how much energy remain in the spring? So if we take a difference of the loading graph and the unloading graph, this shaded blue area will give us how much energy stored by the spring. Yes, I will repeat that part about the loading and unloading. Look, what does it mean? Say you was having a spring which was having a length of 10 centimeter. You add a load of 5 Newton, the spring is now 12 centimeter long. You add a load like example 10 Newton, the spring is example 14 centimeter long. You add a load example 15 Newtons, The spring is example 16 centimeter long. So when we work out the extension, the first part, what is the extension here? 2. The second part, what is the extension? 4. And the third part, what is the extension? 6. This is a loading graph. Means this part. When you add a load, the extension was also increasing with the same amount. But when you unload means you remove the load. So example, so this was 5, this is 10, and this is 15 and 20. Example, we start to unload from 15 and the extension was there 2, it was there 4, it was there 6, then 8, 10, and so on. So when the force was 5, the extension was 2, mean this point. When the force was 10, extension was 4, this is a point. When the force is 15, the extension is 6, so this is a point. So we got a straight line. But when we start to unload, when we start to remove the load, so for example, when I remove the load, like from it was 15, I remove the load and make it 10. So when I will make it 10, even because at 10 it was the extension was 4. But now what will happen? At 10, the extension will not be 4, it will be more than 4. Then when I remove the load to 5, the extension should be 2. But it will not be 2, it will be more than 2. But when I remove the load, no load is there, the extension is 0. So when I join these points for the loading of the spring and the unloading of the spring, I find a difference. So why there is a difference in the loading and the unloading graphs? Because when you add a load, you do more work done. But when we remove the load, the work done is by the spring. So spring does not do the same amount of work done. It will have a different work done. It will have a less work done. So spring is doing less work done compared to what you did, because what will happen, some of the energy is stored in the spring. When we were adding a load, we were doing a work. But when we remove the load, the spring is doing a work. So work done by us and work done by the spring is always different, because some of the energy stored in the spring. That's why we say that the loading and the unloading graph will never be same. The work we did will always be more as compared to work done by the spring. Is it clear? So this is the work we did. This is a work by the spring. So when we take a difference, we get how much energy stored in the spring. If the elastic limit not exceeded, the line be same, it will show us. No. If within the elastic, you mean the limit of proportionality. Even if it is beyond the elastic, when we cross, even within the elastic limit, the work done by the spring and the work done on the spring will always be different. It will always, loading and unloading graph can never be same. Even we are within the limit or we are beyond the limit of elastic limit or a limit of proportionality. Is it clear, the concept about the energy stored in the spring? Anyone having a doubt or a question? Why the loading and unloading graphs are never be same? Because what will happen when we add the load? When we are adding a load, we are doing a work done on the spring. So force is there and extension is there. When we are adding a load, we are doing work done on the spring. When we are removing the load, spring has to do a work done. Like spring has to pull the object upward. So spring does not do the same amount of work done because spring stores some of the energy as an internal energy or a heat energy. So when spring do a work done, the work done by the spring will be different. The blue line is representing work done by the spring, and the red line is representing work done by us. So there will always be a difference between the loading and the unloading graphs. So this is the loading means we are doing a work. Unloading, this is a work done by the spring. So why work done by the spring is not same as work done by us? If we did a work done of 100 joule, the spring should also do a 100 joule work, but spring stores some of the energy and it become a heat or an internal energy. That's why the loading and unloading graphs will never be same. We can calculate the loading and unloading graph area. Like example, if I want to calculate what is the work done by us when we are loading, so we'll take the area of this graph, area of full graph. That is work done by us when we are loading. When we are unloading, say this is a graph for unloading. So we'll take area of this graph to know how much work is done by the spring. This is when unloading. So if I want to know how much energy remain in the spring, so I will get the area of this part, say R. I'll get the area of this part, work done by the spring. If I want to find how much energy remain in the spring, I will simply use R minus S. That will show how much energy is stored by the spring. Is it clear, this concept? So loading and unloading graphs can never be same. It will always have a different because the work done by us is not same as work done by the spring. So if we load and unload within the elastic limit, like example, we have a force in extension and it is a straight line. That's a limit of proportionality. And then we add a load, the extension also increase. So this is the elastic limit and we return back. So this will be the unloading graph. This is the case when we don't cross the elastic limit. But what if we cross the elastic limit? It means the spring will deform. Spring will deform. The extension will not be zero when there is no load attached. So if we are beyond the elastic limit, so this is the elastic limit and we cross the elastic limit. In that case, when we unload, so this will be the unloading graph. So it will not return back to the same original length. So it will have some extension when there is some, there is no force like applied on the spring. Still, it will have some extension because it is deformed permanently. So beyond the elastic limit, the spring will deform and be called as a plastic deformation. Within the elastic limit, the spring will return to the same original length and we call that as a elastic deformation. So this is an example for loading and unloading graphs for the plastic deformation. And this is the loading and unloading graph for the elastic deformations. How do we make an unloading lines? Unloading lines, if you want to sketch a graph for unloading lines, it should always be below the value. If extension is on x-axis, then it will be below the value, like force and extension. If the extension on y-axis, then it will be above. Like if you have a graph in which you have force on, if you have a graph in which extension and a force, in that case, if you want to show, then the line should be above the original line. So it is like the extension axis, closer to the extension axis, the unloading graph. So this will be unloading, this is loading. Here, this is loading, and this one is unloading graph. The term plastic deformation means the spring has deformed permanently, so it does not return to the same original length. So when it does not return to the same original length, we call that as a plastic deformation. So when you draw an unloading graph, that it will not return to the origin, it will have some extension when there is no force applied. Is it clear? How the unloading graph above the loading? It depends on the extension axis. If you have extension on y-axis, then you will draw above. If extension is on x-axis, you will draw below. So it totally depends on the extension axis. How can we not still attach